The air route over the Himalayas forgave much, but not basic gas physics. In the autumn of 1943, transport aircraft were exploding in the freezing air without a single shot from Japanese anti-aircraft batteries or fighters. The crew would simply register a drop in pressure in the fuel lines and a slight vibration near the wing root, after which a tiny spark of static electricity from the generator met a concentration of high-octane aviation gasoline vapors and tons of duralumin scattered in pieces over the jungle. This aircraft was the Curtiss C-46 Commando, the heaviest twin-engine airplane of the Second World War. The machine, which could carry a greater volume of cargo than the four-engine heavy bomber Boeing B-17 Flying Fortress, consumed its own crews because of a single engineering paradox. The mystery lay in why the transport, whose cargo compartment held 65 cubic meters of space, equal to the volume of a substantial city apartment, had been designed with a deliberately dead aerodynamic weight that ultimately turned its wings into sealed powder kegs. The answer lay not in military transport tactics, but in the financial ambitions of one particular individual and the corporate economics of the late 30s. The chief designer of the Curtiss-Wright Corporation, George A. Page, Jr., hated ceding market share. In 1937, what took shape on his drawing board was not an army truck in khaki, but the luxurious 36-seat passenger airliner Curtiss CW-20, intended to break the monopoly of competitors from Boeing with their Model 307 Stratoliner. Commercial aviation demanded flights at altitudes above 20,000 feet, above storm fronts, which meant only one thing: a fully pressurized cabin. Page understood that a conventional circular fuselage would not provide enough volume below the deck for the baggage of affluent passengers whose tickets were supposed to cover the colossal operating costs. He therefore made a technical decision that forever defined the grim fate of the design: the double-bubble fuselage. Page mathematically mated two giant aluminum cylinders of different diameters, stacking one atop the other. Their intersection formed a rigid horizontal floor beam that acted as a tie rod, keeping the metal from bursting under the differential internal pressure. This was a complex, incredibly robust architecture that required thousands of heavy steel rivets and massive frames, adding hundreds of kilograms to the airplane's empty weight. By the spring of 1940, the first prototype took to the air, displaying alarming dimensions. Its wingspan measured almost 33 meters, the width of a small aircraft carrier's deck. To haul this mountain of metal through the airstream, Page mounted on the wings two 18-cylinder radial Pratt & Whitney double Wasp engines, each delivering 2,000 horsepower. That thrust equaled the power of 4 modern tank engines, pouring their energy into two 3-bladed steel propellers. Yet harsh economic reality struck the corporation faster than the airliner could complete certification. Europe was in flames, America was preparing for war, and civilian airlines abruptly froze budgets for luxury flights. In September 1940, the United States Army Air Forces purchased the project, redesignating it the C-46 Commando. Army logisticians had no need for velour seats or cabin pressurization. They required only raw payload capacity to stuff jeeps, howitzers, and 40 fully equipped paratroopers inside. At that moment, in George Page Jr.'s office, the deadly trap created by his own compasses snapped shut. The military ordered the complex pressurization equipment to be immediately ripped out of the design to save weight and reduce production costs. But altering the double-bubble geometry itself was physically impossible. It would have meant halting the assembly line and redesigning the airplane from scratch, something the Curtiss-Wright factories had neither time nor funding to do. As a result, the Army transport was condemned to carry enormous aerodynamic drag and extra tons of intricately shaped metal, originally built to contain non-existent pressure. Maximum takeoff weight rose to 48,000 pounds under frontline overload conditions. The airplane was forced to fly at the limits of its structural loads, while the complex geometry of intersecting cylinders and the massive center wing section created deep, unventilated cavities. While Page was signing the aircraft transfer documents to the military, a mine had already been laid inside the thick wing. Rubber fuel lines and carburetors, trapped in a sealed aluminum vault, ready at the slightest leak to accumulate gallons of volatile fuel inside the structure and turn the most payload-capable machine of the era into a flying crematorium. Test pilot Edmund "Eddie" Allen knew the real price of the 18-cylinder radial Pratt & Whitney R2800 engines. On the factory test stand, under ideal conditions, they produced a smooth, mathematically precise roar, burning dozens of gallons of high-octane fuel every minute. But the brutal reality of field operations on the border between India and China quickly shattered the elegant factory graphs. When the impossibly heavy Curtiss C-46 Commando rolled out onto the monsoon-soaked dirt strip in Assam, each of its 2,000 horsepower became an uncontrollable instrument of self-destruction. To lift 48,000 pounds off the ground, equal to the weight of 7 fully loaded army trucks, the pilots had to push the engines into extreme takeoff settings that exceeded every established limit. The harsh, destructive vibration from the massive three-bladed propellers, whose diameter exceeded 13 feet, traveled into the steel engine mounts, and then deeper, slamming into the very same gigantic center wing section of complex civil construction. The metal creaked continuously, thousands of heavy steel rivets enduring enormous shear loads every second. And it was here, in the dark space where the wing joined the fuselage, that a silent mechanical catastrophe began to form. Unlike simple, Spartan Army aircraft, this airplane possessed an extraordinarily complex hydraulic system and a dense, interwoven network of fuel lines. They had originally been designed for the stable temperature environment of a passenger airliner, not for the 100% humidity of tropical jungle and the freezing hell of high altitude. Air Transport Command's commanding general, Major General William Tanner, received grim loss reports on his desk every day, each entry under technical cause showing only a blank dash. The transports were not merely crashing into the mountains, they were literally vanishing in the cold sky over the Himalayas. The root of the problem lay in the routine economizing on expendable materials and the total disregard for basic gas physics. Rubber seals and long hoses connecting the huge fuel tanks to the voracious carburetors cracked catastrophically fast from sudden temperature swings. On the ground, in the stifling tropical heat of India, the cheap rubber softened. Yet after just an hour of flight at 23,000 feet, in the unpressurized, freezing cabin, the temperature plunged to -40 degrees Fahrenheit. The lines instantly stiffened, lost elasticity, and developed microscopic leaks. Lethal, high-octane aviation gasoline slowly seeped into the sealed, unventilated cavities of the wing, where Chief Designer George Page, Jr. had simply failed to provide even basic drain holes for venting dangerous vapors. Gas trapped inside the thick aluminum structure quietly turned the wing, spanning almost 1,350 square feet, into a perfect vacuum bomb. A single tiny spark of static electricity accumulating on the skin while passing through a powerful thunderstorm front, or the slightest short circuit in wiring worn by vibration, was enough to trigger an instantaneous volumetric explosion. The pilots dryly nicknamed it the flying coffin, and it was no exaggeration. The crew burned alive in the cockpit faster than the commander's fingers could reach the emergency pressure dump switches. Dry, cynical figures of military logistics mercilessly dictated their own laws of survival. The Curtiss C-46 Commando could physically swallow 6,800 kilograms of cargo into its colossal belly, twice the capacity of its famous and numerous rival, the Douglas C-47. That meant a single successful flight fully covered a full day's requirement in heavy ammunition for an entire infantry battalion. Sergeant loaders, cursing, crammed into the huge fuselage nearly 10 feet wide, not only standard wooden crates of ammunition, but entire disassembled tracked tractors, artillery pieces, and heavy steel drums of thick aviation oil for remote bases in China. Yet this phenomenal internal volume concealed a deadly trap of aerodynamic balance. Because of the original passenger double-bubble architecture, the center of gravity of the loaded airplane sat critically high. If heavy cargo broke loose and shifted even 2 feet during violent turbulence over the mountain ridges, the massive 20-ton machine instantly lost stability. The huge single fin, hastily adopted in place of the prototype's original twin-fin tail, created an enormous side area exposed to the wind. In strong crosswinds inside narrow, rocky gorges, the pilots could not physically hold the heavy yoke with their hands alone. They had to brace their feet against the instrument panel to keep the rudder anywhere near neutral. Flying turned into an exhausting, sweaty struggle against the laws of physics, where the smallest mistake instantly cost the lives of 40 armed paratroopers seated on hard canvas fold-down benches inside the cold, drafty metal tube. The price of this financial compromise was recorded on the 24th of March, 1945, in the sky over Germany. When 72 heavily loaded transports reached the drop line, they met intense barrage fire from anti-aircraft batteries. The structural vulnerability, cynically locked in inside Pentagon offices, revealed itself with absolute mathematical precision. Shell fragments easily pierced the skin and tore open the unprotected fuel tanks. Without the thick layer of self-sealing rubber the generals had deemed too expensive, aviation gasoline instantly sprayed outward under the enormous pressure of the slipstream. The smallest tracer strike turned the huge machine into a blazing torch. In a single day of the airborne operation, 19 aircraft were blown apart. The metal melted and fell to earth solely because logisticians chose to save weight for a few extra crates of ammunition. Engineering had met its stern verdict. The market chews up military triumphs with absolute indifference to spilled blood, turning yesterday's engineering masterpieces into dry financial losses. In the autumn of 1946, the concrete ramps of storage airfields in the southwestern United States were crowded with hundreds of retired Curtiss C-46 commando transports. The residual market value had collapsed to an insulting $20,000 per airframe. For that laughable sum, practically the price of an ordinary farm storage shed, private airlines received more than 20 tons of high-grade aircraft duralumin, an intricate hydraulic system, and 2 heavy Pratt & Whitney radial engines rated at 2,000 horsepower each. A brief but ferociously greedy era of wildcat cargo flying had begun. Entrepreneurial businessmen bought up these gigantic machines in bulk, ruthlessly ripping out the oil-soaked canvas troop benches and trying to cram rows of comfortable passenger seats into the huge double-bubble fuselage. The commercial arithmetic on paper looked flawless. The enormous airplane could easily carry nearly 15,000 pounds of payload, mathematically guaranteeing its owners windfall profits amid the post-war boom in regional flights. Former military pilots took the worn yokes, sincerely believing the Himalayan nightmares of burning center wings belonged to the past. But inside the sterile government offices of the United States Civil Aeronautics Administration, that blind commercial optimism collided brutally with the merciless laws of physics. The agency's chief engineer, Charles Dye, received a direct order to subject the massive military machine to rigorous certification under the new post-war civil standards, and the results of his grueling tests became an instant death sentence for all passenger ambitions of the design. Charles Dye rolled a fully loaded test aircraft onto the scorching concrete of the test range and coldly simulated the worst situation in commercial aviation. Sudden failure of one engine at the moment of maximum angle of attack during takeoff. The physics of the event proved truly catastrophic. As soon as one of the 18-cylinder engines was artificially silenced by cutting off the aviation fuel supply, the remaining 2,000 horsepower on the left wing had to single-handedly pull the heavy machine at a maximum takeoff weight of exactly 45,000 pounds into a safe climb. In that critical second, the curse of the unrealized luxury airliner from 1937 delivered its final blow. The enormous frontal drag of the massive, intricately shaped fuselage, originally designed by the engineers for deep cabin pressurization, created a monstrous aerodynamic brake. The automatic feathering system desperately tried to reduce the drag of the stopped right engine, yet the three steel blades, more than 13 feet long, still acted as a giant metal shield thrust into the dense airflow. Charles Dye recorded a frightening technical fact in the official report. When one engine failed, the heavily loaded Curtiss not only stopped gaining life-saving altitude, it began inexorably to lose it, sinking toward the ground under the weight of its own overbuilt structure. The enormous single vertical tail that pilots had struggled so hard to hold steady in Himalayan gorges now worked against the airplane itself, forcing the crew to push the rudder pedals to the point of muscle cramps to counteract the deadly asymmetric thrust. The United States Civil Aeronautics Administration immediately issued a strict directive, flatly prohibiting the use of this aircraft for passenger transport without an extraordinarily expensive modernization to transport Category T. Private company engineers were required, at their own expense, to install redundant cooling systems, critically strengthen the firewall in the engine nacelles, and completely revise the geometry of the fuel lines. The cost of these mandatory modifications far exceeded the market price of the used aircraft itself, rendering its legal operation on scheduled passenger routes completely pointless. For the vast majority of small operators, this government order meant swift bankruptcy. But for the heaviest twin-engine airplane of the Second World War, it paradoxically became a passport into the harshest niche of global logistics. The machine, forever denied the right to carry people in expensive suits, was sent to haul bloodied carcasses of frozen meat, heavy steel drilling equipment, and crates of explosives into remote regions where questions of acoustic comfort yielded to primitive survival. In the 1960s, the Central Intelligence Agency's secret airline, Air America, actively exploited the phenomenal capacity of these aircraft to supply mercenaries in the impenetrable jungles of Laos, where every kilogram of payload was paid for from the government's black budget. Yet the true, final irony of engineering awaited this airplane in the far north. On the icy expanses of Alaska and the wastes of northern Canada, where air temperatures routinely fell to minus 60 degrees Fahrenheit, the volatile gasoline vapors that had killed dozens of crews over the steaming tropics suddenly ceased to be a fatal threat. The dry Arctic cold instantly eliminated the risk of a sudden volumetric explosion inside the unventilated aluminum center wing section. The pragmatic engineers of the polar cargo airlines, such as Canada's Buffalo Airways and America's Everts Air Cargo, with icy calm, cut out all remaining traces of complex electronics from the fuselage and permanently replaced the delicate rubber lines with thick, reinforced hoses of heavy industrial grade. They cynically forced the transport to operate at the absolute limit of the old metal's fatigue life, coolly ignoring microscopic deformations in the duralumin load-bearing structure. Northern economics dictated extremely harsh conditions. As long as the two massive cast-iron cylinder blocks continued roaring as they turned the propellers, and as long as the 65 cubic meter cargo compartment could accept 40 heavy barrels of aviation kerosene for remote radar stations, the machine would keep lifting into the sky every day. The old steel rivets creaked under the merciless pounding of Arctic storms. The thick fuselage metal became coated with a layer of heavy matte ice and slowly corroded from condensation. Yet the airplane stubbornly continued to earn profits for its owners, even in 2024. The contradictory blueprint of a luxury airliner, permanently disfigured by military bureaucracy, ultimately outlived all its ambitious creators, becoming an eternal mechanical slave to its own extraordinary payload capacity. The owner of the Canadian transport company Buffalo Airways, Joe McBrien, faces a financial anomaly every morning when he signs the maintenance checks for his oldest machines. On the ramp at Yellowknife Airport, at a temperature of -40 degrees Fahrenheit, stand airplanes whose age has passed 80 years. To start the two 18-cylinder Pratt & Whitney engines on an Arctic morning, mechanics require several hours to warm the massive crankcases with heat guns. The 100-weight aviation oil freezes overnight to the consistency of thick black tar, and if the starter is engaged without preheating, the thick steel connecting rods will simply tear the cylinder block apart. The starting process for each engine consumes gallons of expensive, high-octane gasoline before the aircraft even taxis to the runway. The exhaust stubs spit columns of blue-gray smoke. The blades more than 13 feet in diameter slice the icy air, and the old airframe vibrates with such force that the needles of the analog instruments blur before the eyes. From the standpoint of modern aviation economics, operating the Curtiss C-46 Commando looks like corporate suicide. The machine burns about 200 gallons of fuel per hour and demands expensive lubrication of dozens of control linkages, manual valve adjustments, and inspection of the old magnetos. But Joe McBrien coolly ignores the cost of gasoline because he understands the fundamental engineering secret that makes this obsolete design indispensable. The secret lies in the very first mistake made by chief designer George Page Jr., the error that turned the airplane into a laughingstock in the post-war transport market. When Page created the pressurized double-bubble fuselage, he joined two cylinders of different diameters with a horizontal tie beam so that internal pressure would not burst the metal at altitude. That tie beam, intended as a structural member to resist pressure differential, became the cabin floor. It was engineered with such an enormous margin of strength that it turned into a monolithic duralumin slab running the full length of the fuselage. Modern cargo turboprops, such as the ATR-72, are built from lightweight honeycomb composites and stamped sections. Their floors are designed for light cardboard boxes. If Canadian drillers drop a 2-ton diesel generator onto the floor of a modern airliner, the metal will instantly buckle, destroying the primary structure, and the airplane will be written off for scrap. Northern aviation has no patience for delicacy. At dirt strips above the Arctic Circle, there are no forklifts and no heated hangars. Loading takes place in blizzard conditions, when ice-covered steel drums of fuel weighing 440 pounds are literally thrown into the fuselage and dropped onto the floor with a crash. This is where the overbuilt Curtiss design justifies every gram of its dead weight. The thick horizontal beam of the double bubble absorbs the kinetic energy of the impacts without the slightest deformation. The airplane that killed crews over the Himalayas in 1943 because of its complicated wing geometry survives today solely because of its excess mass. Mechanics cynically inspect the belly after rough loading and find only surface scratches on the massive aluminum sheets. Customers pay thousands of dollars per flight because no other airplane can deliver nearly 15,000 pounds of industrial iron to a 1,200-meter ice strip hastily cut straight into a frozen lake. Each flight of this veteran represents a complex task in metal fatigue. Engineers of the Civil Aviation Administration of Canada strictly require non-destructive inspection of the airframe's load-bearing elements. Technicians use ultrasound, checking the wing attachments and the massive fin. They search for microcracks in duralumin alloy 2024, which has endured extreme loads for 8 decades. Metal fatigue cannot be cancelled by directives. The alloy's crystal lattice inexorably breaks down from the vibration of 2,000 horsepower, the brutal impacts of the landing gear on frozen ground, and sudden temperature changes. In the joints between steel rivets and aluminum skin, galvanic corrosion develops out of sight. To keep the machine flying, the owners buy retired fuselages across North America. The old aircraft graveyards in the deserts of the state of Arizona have become the only source of legal parts. Mechanics drill out wing sections from dead airplanes and integrate them into living machines. This is absolutely cold mechanical transplant surgery, with not the slightest trace of sentimentality. When an old-style hydraulic pump finally fails and cannot be rebuilt on a lathe, the company simply writes off another airframe. No one erects bronze memorials to these airplanes. Metal that has completely exhausted its design strength is ruthlessly cut with an oxyacetylene torch into shapeless pieces. The heavy Pratt & Whitney piston engines, which once cost millions of dollars in today's money, are sold for scrap or handed to random collectors for mere pennies. The story of the heaviest piston engine twin of the Second World War ends on the dirty concrete of maintenance areas, among sticky puddles of used oil and sharp aluminium shavings. The irony of fate lies in the fact that the ambitious project of a luxurious, high-altitude airliner, which was meant to carry wealthy passengers with crystal glasses of expensive champagne, entered history as the most brutal, dirty, and uncomfortable truck in the history of global logistics. Chief designer George Page Jr. sincerely tried to create an absolute masterpiece of engineering comfort, but the ruthless economics of war and the cold laws of aerodynamics turned his elegant drawing into a primitive tool of rough survival. The C-46 commando transport proved to the entire market that in commercial aviation, the Survivor is not the most elegant or the fastest, but the one whose structural members can endure the maximum amount of abuse from careless loaders and pitiless nature. As long as the pure financial gain from hauling heavy drilling equipment to the far north exceeds the colossal costs of aviation gasoline and replacement cracked cylinders, these massive aluminum monsters will keep tearing the dead silence of the Arctic sky with their thunderous low roar, burning hundreds of gallons of scarce fuel per hour and continuing to pull their endless load without the slightest hint of a deserved retirement in a museum hangar. Senior mechanic of Evert's Air Cargo, Alan McLean, regards every Curtiss C-46 Commando that arrives on the ramp in Fairbanks not as an aviation legend, but as a rapidly deteriorating warehouse of wearing parts weighing 14,000 kilograms. In the reality of polar commercial logistics, the life of one machine is sustained solely through the ruthless dismemberment of another. When inspectors of the United States Federal Aviation Administration revoke the airworthiness certificate of yet another aircraft because of through corrosion in the spars, the airplane is towed to a gravel pad. McLean and his crew arm themselves with pneumatic cutters and hydraulic jacks. The merciless cannibalization begins, where every part carries a strict dollar equivalent. The duralumin skin is already worth nothing, but the giant landing gear struts, built to absorb the impact of 22 tons striking frozen runway, are valued in the tens of thousands of dollars. To extract these cylinders from their wells, the mechanics must cut away sections of the wing with a torch. Molten 2024 alloy drips to the ground, exposing the intricate internal structure of the unventilated center wing section that George Page Jr. designed in the 1930s. The sealed volume that once turned the transport into a vacuum bomb over the Himalayas is now packed solid with dirt, ice, and a thick layer of black anti-corrosive compound. The prime quarry for McLean remains the two massive Pratt & Whitney R2800 radial engines. Factory production of spares for these voracious 18-cylinder engines ceased at the end of the 1950s. Today, the mechanic is forced to hunt for each of the 36 steel valves, dozens of spark plugs, and every piston ring on the global market of aviation scrap. The cost of a restored cylinder assembly reaches $3,000, while a complete overhaul of the entire engine requires a gigantic sum confidently exceeding $150,000. The economics of the process look insane when the real consumption of fluids is taken into account. In cruise flight, the engine legally burns up to 4 gallons of aviation oil per hour simply through blow-by, spitting it out as blue-gray smoke. Mechanics must manually pour 40 gallons of fresh lubricant into the tanks before every flight. But McLean knows there is no alternative. Modern lightweight turboprop engines are physically incapable of withstanding continuous operation in extreme icing conditions, when chunks of ice and dense snow are sucked into the air intakes. The Curtis's cast-iron crankcase grinds up that ice without the slightest consequence to structural integrity, paying for this toughness with a monstrous appetite for scarce 100-octane aviation gasoline. The point of no return for a specific airframe arrives not in turbulent skies, but in the offices of insurance companies in London. Financial analysts who have never held a greasy wrench methodically calculate risk models. As soon as microscopic metal fatigue in the tail attachment fittings reaches its limit, the insurance premium for a single flight instantly rises to a level that renders commercial hauling unprofitable. This is cold mathematics, completely devoid of sentiment. McLean receives the official order to shut down the engines of this airplane forever. The crew of technicians first drains the remaining precious oil, hydraulic fluid, and gasoline. They then carefully remove the Hamilton Standard 3-bladed propellers, more than 13 feet in diameter, each of which fetches no less than a new European automobile on the secondary market. The instrument panel is brutally torn out of the cockpit, leaving dead bundles of severed copper wiring. A week later, all that remains of the largest twin-engine transport of the Second World War is a hollow, gnawed skeleton. The icy wind howls through the empty cargo compartment of phenomenal volume, 2,300 cubic feet, where armed paratroopers once sat in silence before their fatal jump across the Rhine. The metal skeleton, from which the mechanics had cut away everything of market value, is sold to local scrap companies at the fixed price of 18 cents per pound of weight. A heavy Komatsu diesel bulldozer rolls up to the empty fuselage and ruthlessly crushes with its steel blade the innovative double bubble profile that had once been developed to maintain ideal cabin pressure in a luxurious passenger airliner. The thick horizontal floor beam, which for decades had withstood brutal impacts from diesel generators, bursts with a deafening screech under the relentless pressure of the hydraulics. The steel rivets that had given the machine its colossal aerodynamic weight fly out of their holes with a ringing sound. Aluminum melted in the 1940s at factories in New York is fed into a smelting furnace to be turned into cheap construction sections. The paradox of the Curtiss C-46 Commando closes with absolute zero. The airplane born to seize the luxury transport market from Boeing was disfigured by hasty military specifications, killed hundreds of pilots because of a structural blindness to gas physics, was rejected by civil aviation, and ended its life hauling dirty barrels in the far north. The fate of this metal was always decided by 3 factors: falling oil pressure, fatigue stress in the frames, and the dull cost per ton-mile in an accountant's ledger. The president of the Curtiss Wright Corporation, Guy Vaughan, stood at the large window of his New York office in the autumn of 1946 and looked at the dry financial reports that drew a line under the most ambitious aviation program of the decade. On paper, the figures looked triumphant. During the war years, the company's factories had produced 3,181 examples of the heavy transport Curtiss C-46 Commando. Government Army contracts had brought in hundreds of millions of dollars in net revenue. But Vaughan, an experienced industrialist and hard pragmatist, understood perfectly that this apparent triumph was only a temporary wartime anomaly, generously paid for with emergency taxpayer money. On the desk before him lay a detailed analysis of the post-war civil market, prepared by leading Wall Street auditors. This massive document, with dozens of tables, was the death sentence for the entire Curtiss aircraft building empire. While their main competitor, the Douglas Corporation, successfully and extremely cheaply converted its light military transports the C-47, into mass production passenger airliners, the DC-3, Curtiss's heavy duralumin monster proved completely uncompetitive under the harsh commercial demands of peacetime operations. The reason lay in that very excess dead weight of the complicated structure that chief designer George Page Jr. had built into the project back in 1937. The unique double-bubble fuselage profile, which required tens of thousands of extra steel rivets and the use of massive frames, made conversion and production of a single commercial aircraft 40% more expensive than those of its rivals. Private regional airlines knew how to count every saved cent without mercy. The cost of high-octane aviation gasoline for the two voracious 18-cylinder radial Pratt & Whitney engines, each delivering 2,000 horsepower, instantly devoured any potential profit from selling passenger tickets on short routes. Vaughan urgently summoned the board of directors and the leading engineers, demanding a radical plan to reduce the airplane's empty weight. The technical department's answer was uncompromising and mathematically cold. The complex geometry of intersecting thick aluminum cylinders could not be altered without completely destroying the airframe's load-bearing scheme. The heavy metal dictated its own harsh rules, utterly ignoring the financial desires of company management. To make the massive machine profitable for private carriers, an entirely new fuselage would have to be designed, which meant capital investments amounting to tens of millions of dollars and years of new wind tunnel testing. But the Curtiss-Wright Corporation no longer had either the time or the free financial reserves. The global aviation market was rapidly filling with giant, four-engine airliners capable of crossing oceans without refueling, while domestic regional services were firmly seized by cheap and efficient twin-engine Douglases. Large institutional investors began to panic. Share prices of what had once been the greatest American aviation corporation inexorably slid downward on the New York Stock Exchange. Understanding the inevitability of collapse, Guy Vaughan made the only correct, but incredibly painful, corporate decision. He ordered a complete halt to all ongoing development of civil transport aircraft. The machine that had originally been intended to become the flagship of acoustic comfort and pressurized luxury had forever killed the aircraft manufacturing division of its own company. In the spring of 1948, the Curtiss-Wright Corporation capitulated to the harsh economic laws of the market and sold all its airframe assembly facilities to North American Aviation. The irony of fate lay in the fact that the industrial giant that had created the heaviest twin-engine airplane of the Second World War was forced to leave the aircraft-building business forever, transforming itself into an ordinary contractor, producing spare parts, propellers, and aircraft engines. The engineering dead end built into the wing root and the double-bubble fuselage profile acted as a powerful, delayed-action financial bomb. When the last brand-new Curtiss C-46 rolled out of the assembly hangar, an invisible layer of corporate bankruptcy already lay upon its smooth skin. Those same sealed, unventilated cavities of the massive center wing section, which had accumulated volatile gasoline vapors and burned crews alive over the icy peaks of the Himalayas, had now finally blown up the developers' budgets. Harsh commercial aviation never forgives compromises between aesthetics and cold physics. George Page Jr. had sincerely wanted to create a pressurized palace for wealthy passengers, but Army bureaucracy had ordered that palace turned into a heavy assault truck, brutally stripping the project of its vital cabin pressurization system. This mechanical hybrid could not be financially efficient in either environment. It was too heavy and too expensive for an ordinary passenger airliner, and too complex and maintenance-sensitive for a simple front-line transport. Its intricate hydraulic system, consisting of many miles of thick copper lines and dozens of sensitive valves, demanded constant attention from highly qualified mechanics who physically did not exist at forward dirt airstrips. The cost of replacing a single hydraulic hose ruptured by vibration in the Asian jungle was measured not only in thousands of government dollars, but also in the lives of real soldiers who did not receive wooden crates of artillery shells on time. Pentagon logisticians hated the airplane for its constant breakdowns, and Wall Street civilian accountants despised it for its insatiable appetite for fuel. Decades after Guy Vaughan signed the legal documents liquidating the aircraft factories, scattered remnants of the fleet continued their grim cargo work around the world. Cold duralumin does not know that the corporation that once created it no longer exists. In the dense forests of Colombia, local smugglers loaded pallets of illegal cargo into the huge fuselages, well aware that no military radar could detect the heavy 20-ton machine flying at a maximum altitude of only 100 feet above the treetops, while the two worn-out Pratt & Whitney engines drowned out the sounds of the nighttime jungle with their thunderous roar. In the far north of Canada, these same old airplanes daily punched through dense cloud cover at minus 58 degrees Fahrenheit, laboriously carrying massive diesel units for remote diamond mines. Every flight of these disfigured machines represents a living refutation of the original engineering concept of luxury. The perfectly round windows through which Hollywood movie stars and New York bankers were supposed to look in comfort have long been permanently covered with crude sheets of unpainted metal. The elegant passenger cabin door has been crudely cut out and replaced with huge double cargo doors, whose steel hinges constantly sag and creak under their own weight. The entire long history of the Curtiss C-46 Commando ultimately reduces to the ruthless formula of material strength and the cost per ton-mile. The airplane was officially stripped of its certificate for the future, stripped of all passengers, and forever stripped of factory technical support. Yet the phenomenal strength margin of the horizontal floor beam prevented it from dying on the scrap heap alongside its ambitious creators. This paradoxical airplane became the perfect reflection of the cold reality of heavy industrial engineering, where the beauty of the original drawing always loses to the simple mass of the payload, and the high ambitions of a brilliant designer dissolve without a trace into the black, sticky puddles of used aviation oil on the frozen, cracked concrete of harsh polar airfields.